Impulse Stream Engage. Hey everybody, so last time on the stream we put together the components to train a decision tree to match up different models. One of the things that I did not do on stream was actually build out the decision tree, and then off the stream iFire and I worked together to do a little more in the way of kind of checking and I want to say sanity checking the model. Really quickly, I'm going to go over one of the important things that we did with the decision tree, and then I'm going to go over what the next things that we have to do are. So let me open up our decision tree as it was. The biggest change that we made was previously I had just hard-coded the split value as 0.5 because most of the features were binary. We would either get a 0 for false or 1 for true. And that doesn't always work well when you have features like the position of the arms or something like that, or the location of a bone. And the two approaches that I took, one of them is computing the mean and the other is the median. Median, one would expect to work better because it means that you're pretty evenly dividing your data set into the left side and the right side. You know, half of them have fewer values and half of them have more values. But we ran into an issue where if all the values were the same, or if they were binary and had a very strong bimodal distribution, we wouldn't actually reach the middle point. Basically, we would say, like, if we try value whatever, then all of them are above, and if we try the other value, then all of them are below. So it didn't work out. And the sort of half-hearted approach that I took to solve this is first just try computing the mean and then try computing the median. And then try computing the mean. Mean tends to work better, surprisingly. I think the way that I'm actually selecting the median is incorrect, and that might explain part of it, but this would be pretty intense to actually step through. So maybe I'll come back and fix it up. But today what I want to do is I want to actually build out the evaluation. So the way that we train the VRM remapper when we call train is let me open up main scene. Main.tscn basically has a bunch of child characters inside the VRM remapper, and all these are skeletons with some kind of IK setup. Then when we want to call train, we say, like, okay, let me look at all the child objects, select their skeletons, and then produce features from those skeletons as long as they have the same bone names. So our assumption is that if two bones have the same name, then they are in fact the same bone. This is a bit of a loaded assumption because if you think about it in a little more depth, it means that if they have different names, then they are different bones. And that's not necessarily the case. Like, you could have, in the case of, I think Big Vegas here has a skeleton with like New Vegas _ hips and New Vegas _ pelvis. And that's like, hips is the same as hips in the other one. There's no ifs, ands, or buts about it. Haha, hips. So this assumption is not right. There are ways to get around this. Like, ideally we would build a clean data set with the actual mapping, and that would be lovely. But for the time being, I'm going to just use the cleaned data that I put together. Like, I have, 3, 4, 5 characters that I put. So I'm going to throw those 5 in. We're going to get a big data set out of all of them, and then I'm going to build an evaluation system that basically produces that huge swath of data and then incrementally removes one of the models and evaluates how well we match up the bones between them. So this is called leave one out evaluation, or one cross validation. I actually forget the number, like if one refers to the number left in or number left out. But like 5-fold cross validation would mean you split your data into 5 chunks, you leave one chunk out, and that becomes your test set instead of your training set. So let's actually put that together. First, I think I need to go through the rigmarole of like importing or adding the child scenes and stuff like that. So we've got AJ. I'm going to open up Claire. All right, I need to actually drag Claire into the scene and then open the scene now. Open anyway. And then I just do a little bit of cleanup. Like, I move the skeleton around and rename it to skeleton and skeleton 3D. I should probably honestly just like just bite the bullet and like change it so that everything uses skeleton 3D, but I'm not gonna do that. At least not now. And then I'm gonna jump back to my main scene, get rid of the old Claire node, and then instance our new child scene, which is Claire, TSCN. And I think, yeah, I've got Abe also in here, so I'm gonna instance that child scene, instance child scene. I think I might have done something, well, cleaning up the branch, because I see some older AJ nodes, but that's okay. So I'm going to instance Abe. I'm going to instance AJ again. So get rid of AJ. And then instance Abe. Sorry, instance AJ. So the interesting thing here is you'll see that they have different scales. And this is actually something that I kind of want. It looks a little ridiculous, but the purpose behind these different, like, vastly different scaling things is we want to be able to say, like, if somebody happens to import a model that's much larger than the others, then we would like it to be robust to that kind of thing. So one other thing that I maybe should do is rotate this 90 degrees or something like that, or just so that we don't get overly dependent on the relative positions, but we can always add noise to the data set a little later. I'm going to instance another that I made, which is James, Jasper, and Joe are the next ones. Actually, let me just drag those in. James, Jasper, Joe, Jingleheimer, Schmidt. Drop these in. Actually, it makes for a very convenient setup because I can just like shove this over, skeleton, delete. For all these skeletons, I actually did go through and like basically make default rest poses, but that won't necessarily be the case in the future. So all I have to do is advance each of the animations by a frame, and then they'll get into their old state. But I don't want to train on that because I don't want to match up there yet. All right, so we've got James, that's done. Claire is done. Ajay, don't save. Abe, don't save. James, we have handled. Yes. Now Jasper, open anyway. Thank you, Jasper. To skeleton, delete, and save scene as. This is Jasper. Done. Jasper, thank you for your service. And Joe. It's always, I don't know if anybody else feels the same way when somebody says their name, or when you have to read your own name. It just feels quaint to me. Save scene as Joe. There we are. And now I will instance each of these child scenes. Instance child scene James dot tscn. Instance Jasper tscn, and then instance child scene of Joe. So I believe one of the first things that we do is perform the train, and with 6 models, it's gonna be a bit of an ordeal, I think, for all this training data to get produced, but I'm still curious if it can work. So I'm gonna start by turning this down. I don't think that the depth of the 3 is gonna be the limiting factor. I think it'll be more just the amount of data that we've got, which is surprising because like when we started up, I totally thought that we would not have sufficient data for marking things as same or different, but you know, let's push the button and see how it goes. So we've kicked off training, which is surprising. Or which is not surprising, but yeah, I don't know where I was going with that thought. It has taken a little longer than expected, but I think most of that time is spent actually like preparing the data, which is totally fine. That's like, given the number of pairs that we're making, it makes sense to me. Okay, and here's our trained model, which is much smaller because I capped the depth of the tree, but it looks like we've got some still interesting stuff. I am going to replace our old decision tree because, you know, that seems like I guess I really don't have to. But I am going to check to see if we call train again on decision tree. I don't remember if we replaced the tree or not. Yeah, calling train with samples. I believe we do replace our root. Yeah, so we will split, best feature, best impurity, left samples, right samples. Then we split the data, create the new script. I actually should update this for GDScript 4. Let me rephrase that. iFire, thank you for updating the script to Godot 4. There's still some stylistic things that come from an earlier version of Godot. Like this was written with GDScript 3, or sorry, GDScript original in mind, or Godot 3. So there might be some stylistic things that we can improve. But it looks like we're okay. So train actually does return a new, returns itself, which maybe for the sake of like consistency I should undo, but at the very least, if we train something and then train it again, we will replace the model, so we don't have to worry about like reinitializing or anything like that. So we've got this trained model, and now I want to build the evaluation. There's a bit of an open question I want to say about whether evaluation should be built into the training or not. It kind of should be, I think. So maybe I'll just put in a parameter like cross validation folds equals 0 by default. And then if cross validation is set to greater than 0, then we'll actually do the divvy where we pull out whatever percent of the data and make it like use that for our evaluation. So this is trained on everything. What I'm gonna do is at the final steps, hang on, let me think about this. Let me define an evaluation function first. Yes and no. Like, I don't know if I want to make evaluation like a separate operation or not, because it's actually pretty simple. Well, it's simple, so let's do it. What's the worst that could happen? So func evaluate, and then I'll have the, I think we have labels and examples separately. Yeah, so evaluate examples, which is a list of, oh, do we have array in Godot, and then labels, which is also an array. And this, I think, is going to return a confusion matrix. So return result set, yeah, results. And the evaluation, results, is going to be dictionary. We're going to return a couple things. There are like a ton of ways to evaluate the effectiveness of a network or of a machine learning algorithm. Let me do a couple of the popular ones are, there's accuracy, precision, F1, things like that, or precision recall F1. Precision is, there are some really good descriptors on Wikipedia, but I'm going to try to lay it out as best as I can. Precision would be, I reject the things that are definitely not the correct result. So if I were very precise, let's say that the green points here, I'm going to pick blue for people with red read color blindness. The blue points are the ones that we want. So this could be our data. We don't know exactly what these blue points are. We know they're points, but we don't know if they're right or wrong. And then the red ones are the ones that we would like to avoid. This Petri dish is just our data set in the wild. If I were very precise, then I could pick, say, just this. And my high precision would guarantee that I'm very likely to pick out results that are correct, and I will reject the ones that are definitely bad. If I had a very high recall instead, I might pick this ring instead, which you'll notice gets more of the points that are correct, but I also get a couple of wrong answers in there. So that's a precision recall trade-off. Another option that some people use is something called area under curve. And I know a few folks that really dislike the area under curve, but I happen to be a fan because I think it gives good info. So you have the true positive rate, or the number of true positives. I'm just going to call it TPR. And then the false positive rate. For, I don't know if I need to define these for people or not, but a true positive is when I say, yes, this is spam, and it is in fact spam. A false positive, which I'm sure you've heard before, is when I say, yes, this is spam, but it's not actually that. And then something similar applies for the false positive rate. If I say, this is not spam, and it is not spam, then that's a true positive. If I say, this is not spam, this is not spam, and it is spam, that's a false negative. So what we can do is we can kind of trade off between the number of true positives that we get, sort of how selective we are and how precise we are. So at the very least, we say, like, if we predict, we can set our threshold. Sorry, I'm going to block this out. There's this this quantity we have called threshold, which is basically if we have a prediction, like not a prediction, but our model says that we have a 5% likelihood that this is spam, and we say that our cutoff for calling something spam is 10%, then those will all be false. What happens is you get this very nice sort of diagonal line, where you're basically just guessing. Like 50-50 shot, you're right or wrong, then you would expect a straight line along this angle. PR. However, if we say that our threshold for something being spam is 0.5, and our model predicts all of them as like not spam, then we would end up at the point sort of down here. Our true positive rate would be very low. Our false positive rate would actually be pretty high. And what we get eventually is a very nice curve. For a good model, we have a curve kind of like this, because it lets us say, all right, we want this much accuracy and we want this much precision in rejecting things or matching things. This is the binary case. It gets a little more complicated when you've actually got multiple labels, and it's not always fair to represent it as a curve like this, but I'm just trying to explain sort of like what I mean when I use these different terms. You can imagine that a perfect model would be exactly a block like this. It would have an area of 1, because no matter where you set your threshold, your model only predicts 1 if it's absolutely sure, and 0 if it's absolutely sure that it's not a thing, and it's right every single time. Like, that would be a perfect model. The task that we've got for our evaluation is going to be taking all these examples and then seeing if we happen to match them with the right thing. So even if you're... let me pause for a second. Since our labels are... our predictions are float values, basically. We can make these floats, we can leave them as the probabilities, which I'm tempted to do. If we leave them as Booleans, then it's actually much easier for us to do some of these counts, because like true positive rate, false positive rate is much easier when you've just got like true or false. You don't have to worry about conversions or thresholds or anything like that. But if you have actual probabilities, like if you have confidences, then you can do something called cross entropy, or you can do another matchup. So I'm going to leave this here, but pick another color. What we output from our prediction for a bone is a probability between 0 and 1. So, and you can imagine that if we have multiple bones, so let's say we're trying to match up finger _r_index. And we have a bunch of other bones that this could be. And for each of those bones, we're actually spitting out the probability. So let's say spine 1. There's probably like very low probability there. Let's say hips. I'm going to say low probability again. Let's say finger underscore L. And we say like, oh, well, this looks kind of familiar. Maybe a finger R. And we say like, this actually seems fairly likely. And then, some values in the distribution for the rest of the different bones. We know that the actual true value for this, pick a light blue, is basically 0 for all these. And then a spike perfect confidence for that. And the way that we can convert, so I think I got ahead of myself and managed to confuse myself. If you're training a deep network, a lot of times what you'll hear used is something called cross entropy or softmax. And the idea is you have one of many labels, and then you can do a neat trick where you convert the output predictions, not just from 0 to 1, but from negative whatever to positive whatever, into this compressed distribution of 0 to 1, such that it actually makes a probability distribution. Then you do the dot product with the actual result, more or less, and sum everything together to produce what's called a loss signal. In the great case, you'll end up with a nice signal where you happen to guess highly. So if my output of the model was something like, I think this is very likely to be a finger and very, very likely to be finger right, but not likely in anything else. That's better for my model. My model's doing better than if I had said, I think this is somewhat likely to be hips and fairly likely to be finger left. Like, you can see that the orange line is a better fit than the red line. So what is all that to say? When writing this evaluation function, like up above, we had built this system for actually mapping between the bones. Remap basically just goes through all the different bones, and then for reasons we start from the root and then match to the tip, basically picking the most likely output for each of them, and ignoring, like, I think we actually do check for duplicates, or maybe we forgot to do that. That might be my fault. Used bones. Oops. Yeah, so we need to do that. So to do, make sure we don't double assign bones. Aha. And this is not even a particularly intelligent way to search because it doesn't maximize like the overall probabilities, but it's more of a weighted, like, prioritize getting the roots right. In any case, we end up with the mapping from the bones to all the best bones. Now, we can evaluate based on this remap function, which is, on the one hand, that's good because it means we are checking and testing our output. It means we're sanity checking our actual results instead of the input model. But it means that if, like, evaluation says that what we just did is terrible, we don't know that it's necessarily a problem with our model training or a problem with the way we're actually doing the mapping. And for that reason, I think I'm going to do the evaluation on train. And then at the end of train, we can call evaluate and pick the best out of all of them. So what should we print out for evaluate? Well, our dictionary could give us a nice confusion matrix. Confusion matrix, again, says like, okay, we always confuse head with something else, or we always confuse hip with spine 0 or something like that. And that's useful for validation, but it takes a little more time to write, and I don't even think that I could visualize it in Godot. Or we could pick another metric like precision or recall or accuracy. And then in that case, we need to decide like, okay, do we define getting one bone correct as precise, or do we have to get it spot on? And I think for our purposes, because we have examples and labels, I think it would be easiest to do a very simple, instead of returning the dictionary, I think it makes sense to return precision recall F1. Yeah, I'm tempted to just return like a tuple of true positive rate, false positive rate, true negative rate, and false negative rate. I don't remember if Godot will return tuples or not. I think it will. But again, I've spent the past week or so building stuff in Python, and terminologically, like I get the syntax a little mixed up. Let me just change this from dictionary to nothing and return results false. Can I do that? No, I cannot. Can I do this? I cannot. Okay, so just single result value. That's fine. And that means that my result is going to have the true positive count, the false positive count, true negative count, and the false negative count. Actually, does this make sense? This basically gloms together all the different bones. It doesn't take into account any priority or anything like that. I'm kind of okay with this idea. Yeah, for simplicity's sake. We can always improve and evaluate later. Okay, so returns the error types, TPR, true positive, false positive, true negative, false negative, for the given batch of results. A perfect classifier would have a true positive of 1 and a true negative of 0, but we can trade off between true positive and false positive later. That'll be the thing that we tweak. Or that'll be the thing for which we optimize. So let's actually run this evaluation now. We have DT, which should be trained. I just noticed that we're allocating this locally. So self.dt, self.train. We do we return DT, but we also pre-allocate it. So I think it's a bad habit to return intern value, because you don't know okay, this is returning it, but it's also mutating internally, and I wish there were some better terminological stuff like there is in Rust. Nonetheless, I got myself distracted. So we've got DT, it is trained. We could take our model here as a parameter and then reuse that, and I think that's what we're going to do, because we can not necessarily assign self.dt. We want to just have evaluate be able to be called separately and give us a result. So for example, I'm going to do actually for index in range 0 to the length of examples. We'll do our prediction equals our model.predict, and then examples at index. And this will be a label of some sort. Generally, it'll be true or it'll be false. And I think, if I remember right, we're just returning the actual label value. Predict should take the label value, or should give back a label value. Probability by category, predict returns, returns a Boolean rather than a label. We should return a label, I believe. I don't know how to actually, probabilities of that, prediction, label name. So this doesn't have to be a bool. Boom, there we go. All right, as it happens, like, because we've been training basically with Booleans, that hasn't been a problem, but in this case, like, our label set could be any of a multitude. So that was probably confusing, and I apologize for adding bad types. Dictionary still holds true, so the predict with probability returns a label to whatever probability. So our label confidence setup is also dictionary, and I think I need to annotate this. Label confidence is label type to float. That should be a little more clear. I do wish that I had some more type info there. Okay. So we've got our VRM remapper. This is going to give us a prediction, which is whatever the label is. We don't know the type necessarily, and I want to kind of keep it that way. And if we have to coerce this to a float. Because if it's going to be like, if it's going to be true, I think our labels, sometimes we'll get something like this. So false 0.1, true 0.9. And this means that the prediction is 90% sure that it's true and 1% sure that it's false. I don't think that we actually did that for this case. I think we just appended true and false. So for us, a label is inside the set. I don't remember what the key is for it. In this set of items, true, false. And our prediction is in the set of, actually this is also in the set of true, false. Okay, yeah, this is fine. In this case, if the prediction is true, pass, if else the prediction is false, pass, and then we have if labels index is true, then results true positive plus equals 1, else labels index, results, and this is TP, double quotes, results, we said that it is true and it is false. So this is a false positive. Otherwise, if labels index is, oh, sorry, I'm doing is, but I should be doing equals because this is not an object compare. I could just do if prediction, and I could do if labels, but I think it's a little more helpful to be explicit about equals true or equals false. True. Then results, this is a false negative. Sorry, the label is true, and we said that it's false, so it's a false negative. Otherwise, results tn plus equals 1. All right, and that means that after all this, we have a results table which has the true positive rate, false positive rate, true negative rate, false negative rate. I'm going to go through, and just for the sake of comparison, I'm going to divide by the number of results. So that gives us a like 0 to 1 for all these things, and it just makes it easier. Like if we have more data, like we don't have to worry about comparing raw counts. All right. Yeah. So for renormalize, and make sure I make the rates counts into percentages, 2 percentages. All right, our examples is going to be length of the examples, and then rather than doing any kind of fancy iteration, I'm just going to say results TP divided equal to float len, sorry, num examples. And I will duplicate this for each of those. True positive, false positive, true negative, false negative. TP, TP, TN, TN. All right, cool. And I think I'm gonna print this for the evaluation. So like we would expect if we're like running evaluate on our training data that things would be perfect, but because we're capping the depth of the tree, we actually have some issues. Like we're not guaranteed to be 100% accurate. So print evaluate examples labels. Okay. Too few. Oh, and our model is self.dt. Okay. So let's run this again. I don't know what I really don't have any guesses about what our true positive rate and false positive rate is going to be. Place your bets in the comments. I guess, let's see, a perfect case, like a great case would be our true positive rate's enormous, our false positive rate is really tiny, and it's abysmal. Actually, I think I might have made a mistake. So TP, FP, TN, FN. This does not make sense to me unless we had absolutely zero positive results and zero. Actually, what this says to me is we have classified everything as negative, which is possible. Like, I believe it. Let's take a look at the model. So I think I have a JSON formatter, new text file. Hello. And then JSON format. Yeah, let's think about it. Okay, so our topmost feature is feature number 15, impurity index, and our label confidence is false for almost everything. And then false below that, and then false below this, and then... So if you look at these different label confidences, there are very few cases where we actually say that it's true. And that kind of makes sense because when we're doing our training, I think that we sort of dilute the number of true cases because basically we say everything is false. Not everything, but like because there are many more bones that do not match than there are bones that do match, which is maybe to be expected. Okay, this actually makes a lot more sense to me. So the model is indeed predicting false for everything because it's so likely that bones do not match. Ways that we can improve this. We can change the threshold for what we consider, like we can use the probability, and instead of using like predict gives us the maximum probability, and the maximum probability is in fact that they do not match. But we could do predict proba instead, or predict with probability, and say that if it's greater than 0 point whatever, then we count that as like true. And that's not the worst option. I'm inclined to not modify the, well, yeah, I'm thinking that, yeah, I'm going to call this predictions and then predict with probability. Sorry, I should clarify my thought process. I don't want to modify the decision tree or the way that it trains, because I think that predict returning the most likely thing makes sense to me, and I don't want to give it like, I don't want to throw in just another parameter that says like threshold or whatever. Instead, I want predict with probability to give back the possibility of an output and then the probability itself. Yeah, I'll do that for now. And what this means is if we get into the nitty gritty, like if we get really deep into the tree and it does something like we make a right and then we make a left and we end up in this tree, we can see that there's not much we've got other than this is definitely false. But if we get into one of these other trees, then there's a larger probability. One option is we can downsample and not put in as many negative results, which is a decent option. I remember reading a paper about that a while ago, but the details elude me. It was something like if you artificially upsample, it's bad. If you artificially downsample, it's slightly better, but it's still not great. So instead, I'm going to use the predict with probability, and then I'm just going to pick a very low threshold. So var prediction is going to be true. Sorry, prediction equals predictions. True is greater than 0.1. And again, our returned probability, say like, gives us back the label, and then predictions is, so it gives us back the label name and then the output and then the probability. For example, if we also, like if our labels were instead of true false for something like leg, face, butt, then we would get out leg 1, face 0.1, butt 0.8. So very likely to mix up leg and face, but we're fairly confident that this is a butt, which is something that people say to me all the time. So in this case, prediction, what is the probability that this is true? And in this case, what is the probability that these two bones are the same? And we're just really cutting down our threshold for true. So let me push the button again and take a drink of water. Okay. I have not profiled this, but I think most of the time is spent just gathering. Oh, hello. Aha. So in this case, our prediction doesn't actually have a true inside of it, and that's my fault. So our prediction equals false, and that's just because we have a case where we reach a leaf node and it is never true. If predictions that has true, then there we go. I'm also going to make a note for future self. Map from the bone prediction same equals true to a probability. And then evaluate as false positive, true or false positive, positive negative. Document your code, kids. Entirely unrelated. I just got a new monitor arm and I'm kind of excited about it. Hopefully I can print out or model a microphone mount. Oh, here we are. So this is still really low. The true negative is tiny and the false negative is very tiny. So my inclination, I'm gonna, just to make this a little faster for us to debug, I'm gonna move this model into here because we just trained it. And then I'm going to run evaluate inside of this. So self dot, oh no, we still need to load the data. So never mind, I can't do that. Options for making this faster to evaluate. I could cap the amount of time we spend. Even if I like cap the depth of the tree, biggest chunk of time is just spent producing the training data, so that doesn't exactly yield a lot of savings. Instead, I'm just going to say, is there a non-zero chance that it's positive? And hopefully that'll give us a couple of cases where we're correct. All right. I should probably throw in a breakpoint just so I can actually see what the predictions are. I don't think that it's... No, it is all negative, but I don't know what the probabilities are. It would be good to see like the distribution of positive versus negative, though I have my guesses about what that is. Okay, there we go. Our true positive rate is actually still pretty low, and our true negative rate is non-zero, which is a surprisingly good sign. So let me explain this. True positive rate is pretty small. Our false positive rate is 0. So if we say that something is a bone, we are never wrong. Our true negative rate is non-zero. So if we say something is not a bone, it might actually have been that bone. And then our false negative rate is 0, given because of our... Yeah. So what does this tell us? This tells us that we are being very, very picky with our assignment. If we make a guess that something is a thing, we are right. But usually we say like, nope, nope, nope. We're saying no very, very often. Options for sort of shuffling how we do that. We can add more training data. We can reduce the depth of our tree, and that'll make us slightly underfit. I'm reluctant to make this smaller than 5 because 5 is a very, very generous sort of thing. Is already a very narrow tree. I'm going to copy this because it's the best that we've got so far. No, I'm just going to reduce our tree because we can get back to it. Decision trees are deterministic, which is really nice. It means that if you want to, you can basically get back to it no matter what. I'm going to cap it at 2, which is a ridiculous level. And then we'll just see how it goes. I should cache this train data, honestly, but I'm being kind of lazy about it. Or I should maybe use the thing that iFire built and export it, and yeah. Okay, so that was pretty fast. Let's go back to this. So this is about the same. So our true positive rate is pretty close. Our true negative rate, let's look at our actual predictions. So our major feature is feature 15. What is that feature? Shuffle, 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 shuffle. 0, 1, 2, 11, 12, 13, 14. So we're overfitting almost on whether it's the left or the right. We use left to match if it's something, and then the next one, I don't know if we're overfitting on this necessarily, but it's a strong contender. Like, it determines, well, 50% of the time whether we're actually matching things correctly. And the next one is right. I'm going to pretty print this one more time. So let's take our thing and JSON beautify. All right, at depth 0, first we decide left or right. Sorry, left in name. And then we decide, so if left is in the name for both of them, then 1% match that it's true. If there's a mismatch, so if left is not in the name, we go left, and then we look at the position. This is the feature 0, I believe, is the difference in the X position. And then our impurity index, or our threshold is 0. So if there's any difference in position, they're not the same bone. This does not look good to me. Like, I don't like that. it almost says to me that I think there might be a sign error between the two. Like this level of sensitivity to position is just very suspicious, frankly. So I'm going to look back at how we're producing our example data. I wish I could articulate better exactly why it feels suspicious, but it looks suspicious. And if we do, I'm not going to do remap, but I think we had produce feature. Where is it? Make features for skeleton. Here we go. So first we have our result for this. Result. This is all fine and dandy, I think. Get global pose. And then, here we go. Skeleton info, that's fine. But when we produce the features for this, we have our bone name A in the bone descriptors. I think there's something up with this for loop. So we've got our skeleton keys matched up. Each bone descriptor has a big list of the different versions of itself. I'm actually going to write out a comment for this. Given a skeleton, add it to a big list of, given a skeleton, take all the bones and add the properties of each into a huge pile. So index finger left will have an array of arrays of the features for similar bones. Yeah, that's a decent descriptor. Okay, so bone descriptor. I'm gonna move this down here and clean up a little. Yeah. There. Okay. Now, are we correctly producing our training examples? Because we do want the pairwise comparison between basically all of our bones. So we have bone descriptors, the keys, which again should be names, and then this is the feature array, and then we have this feature vector that we're producing for each of them, and it's A minus B, so left minus right, and this is where I suspect our problems might be coming in. This could be 0, it could be negative, it could be positive. I'm tempted very much to map this between 0 and 1, or to do like left less than right, like that kind of comparison. But I don't think that's a good idea, because like these could be position, they could be orientation, things like that. So I'm going to leave this as the difference. But then we need to make sure that our decision tree is good about handling the input features. So I'm going to look at train again. I want to make sure that samples will correctly deal with values that are negative. I suspect there's something related to hard coding or not hard coding, but like kind of assuming that the samples are binary. They are floats, but yeah, the initial mindset was like treating them like 0, 1. So we've got this list of all the samples, and split value is determined by the median of the column or the mean of the column. So if in this case we see our impurity index confidence is that, impurity index is 0. Sorry, this is a subtree. Our threshold is 0. So indeed, this is 0 is being our sort of pivot. It's less than or greater than. And that's desirable. Okay, so indeed, we're handling this kind of okay. Backtracking all the way over. What are some options here? One moment. So we can, our training is okay. Like the features that we're producing are basically sensible. Bone array A, bone array B, that's right. One other option, like I think we've got some duplicate entries which might be slightly diluting our set of things. But that's generally okay. Like duplicate values in decision trees with different labels are generally fine. At least the way we've handled it, because we will just keep track of the impurity for identical results. That's fine. Which says to me that, so for defining on left and right, an option is just like maybe it's worth removing that extra feature. So like, let's not have anything about the properties, and let's just keep depth and children and siblings, and then see how well we do. I'm going to leave all the other things the same because this is science and we should only change one thing at a time. Which I almost never have the discipline to do. Like, I'm the sort that just like, yeah, I could change this, but it's going to take so long to run. I bet I could just like blah, blah, blah. And then I'll change multiple things, and then like, okay, I don't know why it's different. Okay, true positive rate is higher. That's a good sign. False positive rate is lower. That's also a good sign. True negative, false negative being 0. So we saw this before. And I didn't like really think about it, but I think now we are overclassifying bones as being the same, because our false positive rate is greater than 0. So that says to me that this threshold is wrong. Like, we got rid of the really descriptive factors, and now we need to tweak our predictions a little bit. Just as a hack, I'm going to like accumulate the percent true. So debug num true is 0, and var debug num false. Sorry, debug accum true 0.0, and then debug accum true plus equals predictions true. So we're just going to add how much truthiness there is. And then right here at the end, I'm going to print debug accum true divided by float num examples. That'll tell us like it'll tell us the average truthiness, but I might want to do that for just the ones that are true. Like, if something is true, what's the percent? Okay. So I think I have this inside of a... Yep, I got it in the wrong loop. Oops. Shuffle. Debug accum true should not be in here. Whoops. And then this should be... Oh. Hold the phone. Oh, sorry, I am daft. This is not right either. This is at the wrong indentation level. So we should be renormalizing before we return it. Jeez, this is why we can't have nice things. So we were dividing by the number of whatever every single time. And I think that's why we were getting the zeros everywhere. A lot of our base assumptions might be slightly incorrect now. So this is significantly better. Go figure. When you remove bugs, things work better. Our true positive rate is still on the low side. Our false positive rate is higher, and our true negative rate is like okay. But this is the one that I'm curious about. So our true positives 0.12. So let me get rid of this. I think we set our threshold to 0. So if there's any chance that it matches up, then we say that it's true. And now we can actually bump this up a little bit. So I'm going to say 0.1, maybe, just ever so slightly. And then let's see how we do. It could be that we call everything negative now. I don't know. This wasn't really an issue when we did the matching up because we were, how to say, we were just using the most likely match, which means we were dealing with the raw probabilities. But, okay, so our true positive rate is about the same now, so I'm going to go even higher. And I'm going to say, like, I'm going to go bonkers. I'm going to say 0.5. And then what I expect is I'll see our true positive rate basically fall to 0. And if that's the case, then it means that we need to figure out a good threshold. If it doesn't go to 0, then we have some cases where the model is absolutely confident. Yeah, so this is a good sign. It means that we're being very careful, and we just have to find the right threshold for true positive or false positive. You'll notice also that the false negative rate and true negative rate sum together to 1, which is par for the course. But what this tells me is that we can hunt around for a quote-unquote best value. Our options then are, and this is one of the reasons that I really like ML. We can do this in 2 ways. We can cut out a chunk of our data in cross-validation and then evaluate on that, or we can cut out a chunk of our data and use it on the validation step to pick out the best hyperparameter, which kind of makes sense to me. I might do that approach because we have so much, we have this combinatorial explosion of data. Or we can just hunt around and like pick a prediction value, like meh. But with that said, so we're calling evaluate now. I'm going to deepen the tree a little bit because I think that'll give us maybe more fine-grained control over, or fine-grained resolution. I think it'll give us better results. We're very much averaging out things like totally here. And if leaving that threshold is like 0.5 and then deepening the tree gives us better results, then great. Looking back immediately at that sentence, I don't know if it made sense, but okay. So the true positive rate has not changed. So what I'm going to do is I'm going to take this, I'm going to jump back into VS Code, and I'm going to prettify this JSON, beautify, and then look at our true threshold. So 0.007, 0.15, just look at all the true. 0.001, 03, 06. So this is actually quite, feature 7 is doing a great job. And so we're kind of splitting hairs. It might make sense for us to pick something as small as, honestly, as small as 0. So if, no, that's not right. But something really quite tiny. I'm going to pick a threshold of 0.01. And then we can come back and reevaluate. So 0.001. I'm going to run it one more time just to see how our true positive rate, false positive rate is. And then we can go on the hunt for ideal values. Or then we can like build out our evaluation a little more. Or our cross-validation. That's what I wanted to do. All right. True positive rate is still high. Like, I don't like how high this false positive rate is. I would like this to be much smaller. And then our true negative rate is teeny. One thing that we could also do for our evaluation, because we have this nice, because we have the predictions for basically all the labels, we can say, does this fall into the top however many? And that might be a better descriptor. What this would mean is we change our evaluation function to see what percentage of the skeleton we get correct. And that's probably closer to like the real world example. So I wouldn't want to get rid of this evaluate function, because I think it does a better job of like handling, like telling us exactly how well the model does. But like I said, it's not as close to our real world sort of perfect case scenario. Honestly though, like none of this is restricted to the VRM model or the bone matching, so I might just take this evaluation function and move it into the decision tree. That kind of makes sense to me. I quite like that. I like that a lot. Okay, yeah. So shuffle down here to the bottom. I don't know why I didn't think of that in the first place. And now we can leave the dictionary. We can... It's easy enough for us to make... Yeah, I'm going to leave it at this. Giving back the TPR, FPR. I'm also going to make another parameter called threshold. Threshold, which is a float. And this is default to 0.5. This is going to be threshold. Yeah, I'm good with this. I like it. All right, and then this is going to be dt.evaluate. And I don't think, yeah, we need to not do model, but instead do self. That's good with me. And get rid of this. Okay, so the one place that this doesn't get us is it doesn't get us like, we still have the question about like, what do we want to do for an evaluation set? And cross-validation seems like something we still want to do. So I want to handle that now. Do I want to leave this? Yeah, I'm good. I'm going to replace train our model with the cross-validation approach. Or should I change the... No, I think we need we should use this approach, I think, to determine the best threshold value. And we could do that with a more elegant approach, but I think maybe not. I'm pausing and thinking about how exactly... Well, let me start writing the cross-validation. And then we can decide whether we want to apply this to actually doing the train operation or whether we want to apply this to picking a threshold. So first, our shuffled examples. Examples is the examples and then bar shuffled values. examples. And then what we're going to do is we're going to make a separate holdout. So train examples, train values, our test examples, our test values. Sorry, this should be evaluate. Train validation. We could even split it one more time into test, like just take one chunk of those, but I think no. And now we want to shuffle the examples, but yeah, I think I can do this in GDScript. So while len examples greater than 0, var idx, excuse me. Okay, yeah. Index is equal to rand I range. I'm just gonna do rand I, which I think, yeah. From 0 to len examples. I don't remember if it's inclusive or not. So this could possibly be an infinite loop, but oh well. Train examples dot append examples idx, and then train labels. Oops. And then this should be validation labels. Very importantly, don't forget to keep your training labels and examples together. If you split them off by accident and shuffle them, it's just a mess. Labels idx, and now we want to pop both of those. So examples dot remove, I think, remove at index, and labels dot remove at idx. So shuffle examples and split into n sets. The ordering inside of the sets does not matter for decision trees. Let me think about that. Yes, decision trees are deterministic. Order won't matter internally. However, we do want to randomly assign to train and test. That is important, and that's why we're doing the shuffling. We say our num validation, validation set size is going to be the length of the examples divided by cross validation folds. I'm going to think about that. So if it's if we have one fold, then the validation set is going to be the whole thing, and that would be done. If we have 5-fold, then 1/5 of it is going to be the validation set size. So length examples divided by, if we have 2 folds, then each is half. If we have 3 folds, each is a third. Yes. And then our length of examples is while the length of the examples is greater than the validation set size. I think I'm doing something stupid, because if this is 1, then we're going to basically be not having any examples. All right, I need to do, excuse me. What I should be doing is I should just be checking that cross-validation is greater than 1. So if cross-validation folds is greater than 1, then we do actual cross-validation. Else, the I'm going to move these outside. Yeah. Otherwise, and then I have to do this again actually, while length examples is greater than 0, we can just actually extend validation examples dot append array validation examples equals examples, and then validation labels is labels, and then validation set size equals the length of examples. Otherwise, our train examples is equal to examples, and our train labels equals labels. All right. And then we leave both of these as empty. We do have the case where when we're doing our evaluation, we're kind of assuming that it's not empty, so we might get divided by 0, but I'm not going to worry about that too much for now. Actually, yeah, I'm going to take the lazy, stupid way and say validation examples is examples, and validation labels equals labels. And I'm going to make a note at the top. If cross validation folds is greater than 0, greater than 1, sorry, is less than 2, then we reuse validation, the train data, as validation data, which is fine. Not really. Okay, and then we need to train on train examples, train labels, and we should evaluate on validation examples, and validation labels. Okay, perfect. That's our cross-validation done. We should change our main to maybe train on cross-validation folds, maybe 5 folds cross-validation. Normally 5 folds cross-validation actually means you do it like, you divide it up into 5 sets, and then you take out one of the 5 sets and you train on the 4, evaluate against the 5th, take out the second one, validate. So I'm kind of using the wrong terminology here, and I should fix that. I'll run this first, and then I'll fix the terms. So this is not cross-validation folds. It should be like validation set subdivisions or. I was saying I just got a new monitor arm, so I'm going to see if I can model and 3D print a mount for my desktop microphone to get it a little farther away from the keyboard and a little closer to my face. It'll probably mean that I bonk the mic more, unfortunately, but it'll mean that there's not as much background key smashing. Cross-validation does indeed take longer. Oh, I'm going to perform an interrupt because I suspect, yeah, I might have made a mistake. While length of examples is null. Oh no. Oh no. Remove at. There seems to be a problem. Examples is none, or is null. Houston, help. Let me just step over. Okay. Examples is still null, but length of examples is what? 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 I suspect that there's something wrong. Oh, I think I know what. Yeah, I think. Does this operate in place? I need to remember that. Array. Does pop or remove at return a different one? I do not remember if that's in place or not. Remove at. Okay, it's void, so it has to remove it. Acts in place. Okay, that's good. Yeah, that's fine if it has to reindex. That's honestly okay. It could be that the length is not changing. But I don't know why we get this madness with examples being null. I'll just throw in that, and then let's debug. Okay, so it's actually really quick to produce this. I am very surprised by how fast that. Oh, I think Godot might have crashed on me. Yeah. Oh boy. Come back, please. It's a beta. That's par for the course. Fun fact, Command Shift Escape pops up the task manager immediately. Alright, and I want to destroy Godot engine. End task. I actually had an issue with, there we go. Alright, Godot projects, Godot engine for alpha. And let this come back. Vrm Remapper. There we are. Okay. So I don't think I can actually debug this interactively, and I think all my data is still saved, probably. No. Oof. Well, that's okay. These things happen. Remap. Yep, I gotta train examples. Oh no, wait, here it is. I just missed it somehow because I'm daft. All right. So length of examples doesn't seem to be going down. And it's reported in the debugger as null. I can take the stupid approach that prints out way too much info and just say like print the length of examples, which might do it. Let me see if there's just pop at instead. So array, I think there's pop, yeah, pop at will return it and return the element. Can be slower than pop back, that's okay. So remapper, and just do append examples dot pop at index, and then labels dot pop at index, and then we can remove these two remove ats. I am also going to print length of examples here because this has to be decreasing, and if it's not, that explains the infinite loop. There will be a lot of output, but I think that's okay. All right, yeah. Wait. Yeah, it's going down. Still going down. Okay, that's good. The solution that I took is stupid because I am absolutely thrashing the access index because we have to do a linear shuffle for every single pop at. What I should be doing is generating a shuffle, basically. The easiest way I can think of to perform a shuffle is you start at the end and then swap two elements and then you go back. I don't think there's actually a shuffle method. Yeah. There's one thing that's a little unique to data science, which is you have to pair things when you're shuffling. Like if you don't have tuples of data, if you just have like your list of examples and your list of labels, pairwise shuffle isn't necessarily like your regular shuffle method isn't going to do that. And you can hack around this by producing just a list of indices and shuffle the list of indices and then dereference it. Or you can make a method that like shuffles a pair of lists. I think I might do like shuffle pair. So func shuffle examples, shuffle data. Examples will be a list, Labels will be a list. And this is going to return a list of lists. List. Can I do this for? I think I can. Can I not do this? Oh, that's all right. Oh, sorry. No, this is array. GD script. Yeah. Don't forget. Okay. This should be all right. Turn that. Still no. Now the question is, do we do it in place? Yeah, let's do it in place. Shuffle data in place. Okay. Oops. And that should greatly speed up this entire operation, and we'll simplify it. So let's start at the end, and then pick a random element to replace it. So for ID X in range len examples, I believe this is inclusive. Actually, I don't remember if Godot takes. Yeah, it must. Okay. So we have the index, and we want to replace it with a random item. Why am I doing this in reverse? That doesn't make sense. 0 examples. Oh, because it's a. Never mind. I know why. Because it's easier for me to just pick a random number less than index. So var swap index is equal to rand I range between 0 and index. I don't remember if rand I index is inclusive. Index. Rand range from inclusive. Okay, so what we have to do is do index -1. And we're going to go down to 1 instead of to 0. Yeah, because then we will just like maybe be swapping those two values. Actually, we're going to go down to 2. Yeah, I like that. Temp is equal to examples swap ID X, and then examples ID X is equal to examples pulse swap index, and then examples swap index is equal to temp. Just a very simple exchange. Examples swap index. If labels is null, then we'll do the same thing for labels. I'm just always gonna like, when is labels gonna be null? You know, index is equal to labels. Sorry, temp is equal to labels index x, and then labels IDX is equal to labels swap index, and then labels swap index is temp. Very simple assignment. I don't remember if Godot supports double assignment, but I'm just going to check. So examples IDX, examples swap index is equal to examples swap index, examples IDX. No, it does not. You can do this in Python though, which is kind of cool. All right, so instead of this really stupid approach, for which I owe the world an apology, let's shuffle data in place for examples and labels. Yay. And now we can just do this substring operation. So our train examples is equal to labels from, I think we can do slicing in Godot. We have to be able to. Up until negative validation set size. train labels. Examples. Do we not have slicing in GDScript? That would be absurd. No way. Really? Ugh. This is why we can't have nice things. Okay. Examples dot splice split. There's a shuffle method. Okay, well, that's okay. If we wanted to, we could use shuffle, and you produce a list of integers from 0 to the maximum element, and then you shuffle that, and then you use that to assign your values. But I'm not gonna worry about it now. Like, this is absurd. All right, range. What I want to find is the split. Sort slice. Slice might be it. So beginning 0 and going to. I don't think we can do -1 or negative validation set size. Slice 0 to negative validation set size. Let me do a quick search on that array, and then slice returns the array from the beginning to exclusive end, which is good. Clamp to the array size, that's fine. If it's negative, then it's relative to the end of the array. Good. All right. That is indeed exactly what we want. And now validation labels, examples, sorry, is going to be the examples.slice. And this time we're starting from the negative validation set size and we're omitting end because we just want this from the end of the list. And same with validation labels. Okay. I think this is going to be much faster, maybe, but we'll find out. Out of bounds on array 18 swap. Oh, because I'm starting from this. That's my fault. Examples -1. So this will possibly fail if we try to shuffle a list of length 1, but if you do that, it's your fault. Actually, I should do an assertion there. Defensive programming. Okay, cool. So our true negative rate and our false negative rate are pretty similar, but what did I set our validation to? So true positive, false positive are 0, which means that we're not classifying very many things as positive. Oh, I completely forgot something that's actually kind of important. Although this train is, although decision trees are deterministic, one thing that I totally did not do is seed RNG. RNG seed. I don't remember what it is for Godot. Randomize? Randomize? Yes. Okay, this, for anybody that's like cozy with Godot that's watching, remember that randomize, like we do start with the default seed, and if you don't call randomize, then you're going to get the same numbers on the output very roughly. Don't rely on that, but it's a good ballpark. Not that that impacts our training of the decision tree, but it impacts the shuffling of items, which is what we care about. And the good news, at least, is these numbers are different, but they're not very different. That's a good sign. Okay, cross-validation folds greater than 1. And I said I was going to rename the cross-validation folds. I'll say like fraction of data for validation, which I think is a better descriptor. Yeah, I'm good with that. So I'm going to say let's train, and then for our validation, Vrm Remapper, we call train with 0 by default. So that is, so we're using the whole thing. Okay. Pause for effect. Fraction of data, 5. Yes. So if we do something like 10, it'll use about 1/10 of the data. And we can also experiment with like, oh, one thing we didn't even do. So we do split out the train, and we only train it with the example data, and then we validate on the validation data. But we can search for hyperparameters using that as well, which I think is what we should do. Okay. So splitting out, we did the train, we did the evaluate on the validation, and now search for hyperparameter. Data for threshold in 0 to 100, and I think this print like result is equal to dt.evaluate, and we're going to pass in the threshold over 100. So we're basically just stepping 1% at a time. Threshold. And this should be 100.0 because otherwise we're going to get 0 all the time. That's another foot gun. And the thing that we want to maximize is now the question. We can say that our success criteria is true positive plus true negative, or our success criteria is just true positive. Any of these is a good option, and I think that true positive times, I'm going to say 5. Like, I'm just picking some ballpark number. Sorry, let me explain before I talk about the math what I want to do. Our score is going to be result true positive times something plus result, I'll say true negative times like 2. Score is greater than our best. Best score is equal to 0. And if the score is better than the best score, we also have our best threshold. Best threshold equals 0. If our score is better than our best score, then our best score, and otherwise, and our threshold, best threshold equal to threshold. And then at the end, we can print best score, best threshold, best score. And now the question is, best score, gamma. Now the question is, like, how do we want to weight these? Do we want our true positives to be worth way more than our true negatives? Do we want our true negatives to be worth more? I'm kind of leaning towards, I want the true positive rate to be worth significantly more than the I want false positive rate to be very low. So I'm going to subtract off result, false positive rate, and I'm going to score that pretty high, like 5 times 5.0. There's actually a formal way to do this, and I don't remember what it is off the top of my head. So all the data scientists who are screaming and throwing things at their monitor, I apologize. I just don't remember. But I'm going to run this, and then let's see what our best score is. I don't think I actually printed it out, but that's okay. This is going to chug for a second. One of the reasons that we do this in like general data science in IPython notebooks so often is it's useful to be able to just like cache all the data up to a certain point and then like not fret over it. Okay, here we go. Our best threshold is 0.12. That optimally balances the things that we care about, which is kind of neat. And we have our trained model, which is, you know, also pretty handy. So with that, I'm going to take a break. It's been like an hour and 45. I don't know if I'll have more time today to actually work on stuff because I got to do like family things. But beyond that, I appreciate everybody for tuning in. I'm going to commit these changes and then push them up to the repo. And then I'll maybe do some finer grain things at the end of the day. So cheers, everybody, and take care of yourselves.